Hi all, today we're going to talk about frequency. So if you just Google the definition of frequency, you're going to see it says the rate at which something occurs, right? So it's how often something happens. But in waves, it's got a very specific thing we care about. We care specifically about how often a full wave cycle happens. So the easiest way to count how often a wave cycle is happening is wave crests per second. You see how it goes high, low, high. That's one cycle. We just count every high point and divide by our number of seconds. It becomes fairly easy to see how often this wave is coming through. And I think it's easiest to see this in a little simulation, right? So like, let's say we're watching this little green dot. There's 1, 2, 3. And so right now we're at 0.37 hertz, right? This means we see a wave cycle once every 0.3 seconds. So it's pretty slow. Now I can increase the frequency, and you'll see that we get many more of these wave cycles every second. So we're increasing the rate at which this is moving up and down. It can go really, really fast, actually. Yeah, it gets pretty crazy. But something I want to note here is that the increased frequency is not increasing the progression of the wave. The wave is not moving along its length any faster or slower due to its frequency. And this is a little tricky, right? So we often think of frequency as related to speed. But wave speed is just how much distance the wave travels in a certain amount of time. It's measured in meters per second. So if you look at a wave like this, I'm going to pull this one up. This is maybe easier to see. You can see the wave actually moving. And you see that there are two different sliders here. So I can decrease or increase the frequency. I'm gonna make it back in real time. It's more fun, faster. So I can increase or decrease the frequency. So if I increase the frequency, right, you see more waves coming through. And I'm changing the wave length, right? The distance between the two crests is different. Now, the wave speed, however, is totally different. So I can increase the wave speed. You're going to start seeing that what's happening is this is actually moving faster. Now, yeah, so the wave is actually moving faster as it goes through here. So this is important. Oh, one more thing. I can change the wave amplitude. I think I can change the wave amplitude. Oh, yeah. The wave amplitude is not related necessarily to the wavelength or to the frequency. That's just how tall these peaks are. Very small, I can make them very tall. Hopefully I can make them very tall. Struggling to make them very tall. There it is. And that's going to be related to how much force it is, but it's not related to its wave speed or its frequency. Now this is a problem, right? So usually we encounter waves as sound in our day-to-day life. And we have a problem, which is that humans don't see waves. So we don't see how close together the waves crests are. What we typically do is we hear these sound waves as they move by our ears. So like if this stick figure just heard his mom calling, stick man, you see that the sound just goes by us like that. And we interpret that sound as that series of pulse hits our eardrum. Now this is a problem because we get wave frequency and wave speed confused when we hear it. Remembering again, wave frequency is the wave crest per second. And wave speed is how much distance the wave travels in a certain amount of time. Now we're lucky. The speed of sound is somewhere around 700 miles per hour. It stays the same, doesn't change in air. We have this weird thing called the Doppler effect, and that's what we're going to be the subject of our next lesson. The Doppler effect works when you have a moving unit. So let's say this person is talking and they're saying something at a constant pitch. Maybe they're singing. Let's say they're singing. They're holding a note at a constant pitch. And if this green line is our observer, they're hearing this person singing at a constant pitch because they're seeing the frequency is the same. It's getting like 1, 2, 3, 4, 5, 6, 7, 8. Those waves are hitting them at the same time. But now, let's say that this source, the person singing, is moving towards the person who's listening. Now you're going to see that that person is going to hear more. That person is going to hear more and more waves more quickly. See, as they're approaching, the waves hit them more quickly. They're closer packed together. Now, the opposite is true if the singer is moving away from the observer. As the singer moves away from the observer, these waves get more spread out. And this is the effect that causes that noise when like an ambulance goes by and you hear that like wee 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 woo noise. It's higher pitched as it approaches you, and as it goes away, it sounds slower. But this is sort of almost like an illusion. The wavelength is not different. What's happening is the source of that wave has changed.